So today we're going to talk about more systems and specific kinds of systems. We're going to talk about homogeneous linear systems and non-homogeneous. There's section 1.6 that we're going to skip. It's about all about applications, but what I'm planning to do is I'm going to try to make a video of it and show you how to do some of the examples there. But I didn't assign you any homework from that section. But it might be good for you to look over, because I might assign a worksheet project that covers things from that section. So we'll start off by defining a homogeneous linear system here, and then we'll take a look at the types of solutions that would come up, and we'll try to look at graphs of these things too. So we'll stick with 2 and 3 dimensions to be able to try to view them, and then we'll formalize these things and get some theorems figured out, and yeah, and then we'll probably, hopefully, be able to get started 1.7 also. All right, homogeneous linear system is a linear system that has zeros on the right-hand side. All the ax plus by plus cz or whatever it is on the left-hand side is whatever it is, but the b vector that we consider is going to be the zero vector. And if you were, writing to take notes here, I think it would be good to denote that the zeros, when they're vectors, to put an arrow on top. I tried to make it so that they're boldface. So this thing over here should be boldface also. So this says here that if you have a homogeneous system, you have at least one solution, the trivial solution. And the trivial solution is when the weights. So when they say x is equal to 0 in this statement, they mean x1, x2, x3, or however many x's there are. You're guaranteed at least one solution. You're guaranteed at least a trivial solution. And of course, we're going to be concerned about the non-trivial solutions. And so we look for non-trivial solutions, and we do that. We know that there's going to be a non-trivial solution if we go through your system, the matrix of that system, we row reduce it, and we see at least one free variable. If we see at least one free variable, then that system has a non-trivial solution. And the chances are that non-trivial solution will be an infinite number of solutions. Okay. All right. So let's see an example. For this, I'm just going to pull out the book and borrow some examples from the book. So let's take a look at this example, and let's see if we can find any solutions or any non-trivial solutions. Now, remember that from the beginning, you already have one solution that would work for homogeneous systems, right? If x1 and x2 and x3 are all equal to 0, then this is going to work. So now, can we find another solution? Let's see. What we can do is we can write this into a matrix. 1, minus 3, 7, minus 2, 1, negative 4, and 1, 2, 9. And since this is a homogeneous system, the right-hand side is going to be 0. So we can work this out as if there was nothing on the right-hand side, because you would just put zeros there anyways. And any row operations that you would do would still keep the right-hand, the last column, the augmented part, to be equal to 0. So we don't even need to bring that up. And let's go through some row reducing steps here. And this is one of those cases where I would probably take a couple of steps here in this one step, just denoting what I'm doing. So I'm going to say multiply the first row by 2 and add it to the second row. And so I'm going to replace my second row. But in the same step, I can also do the same, since it's kind of making the column 0 for the first column, I can multiply the first row by -1 and add it to the last row. So this is taking 2 steps, and the first row will remain the same, and then here's where we do the work to make things disappear. So 2 times -3 is -6. -6 plus 1 is -5. 2 times 7 is 14. 14 minus 4 is 10. And then for the next step, I'm multiplying this by negative. So +3 plus 2 is 5. -7 plus 9 is +2. And then I could do one more step and just add the first or the second row to the third row, and then replace the third row. Um, 12. So I could stop here. We can do the reduced row echelon form, but if I stop here and say, okay, remember that there's the augmented part is just a bunch of zeros that I didn't write. So if we look at this, these columns is representing, the variables x1, x2, and x3. We see that there's a pivot column in each of these columns. There are no free variables. And so there are no free variables means that we're going to have only the trivial solution. So let's make a note that we notice that there's no free variables here. And when there's no free variables, you can go ahead and conclude, or you can take the steps if you really want to see it. You'll eventually get to this point in a reduced row echelon form, which is to say, if you remember that there's this augmented part over here, which is to say that x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0, and that's the only solution that we have. And that is our trivial solution. So we got what we were guaranteed, but we didn't get anything else. So this has no non-trivial solutions, only the trivial solution. Okay. Any questions? Yes. No, you're guaranteed that you have that as a solution, but you may have other solutions. Well, it's still a homogeneous system. So the homogeneous system just says that your system has zeros on the right-hand side. That's the definition of homogeneous. Now, what we're trying to do is we're trying to figure out what types of solutions are we expecting. So the idea is that if we can row reduce this and we get free variables, then we're going to get solutions that are non-zero. But if we row reduce this and we see that there's no free variables, then the only solution we get is 0. We're guaranteed that. You're guaranteed a solution, a trivial solution, but you're more interested in finding non-trivial solutions. Okay? While we're at it, let's take a look at the graph of these three. These are planes, by the way, or one can look at them as planes. we have x minus 3y plus 7z equals 0, minus 2x plus y minus 4z equals 0, and 1 plus 2, let's call that x, plus 2y plus 9z equals 0. So these are three planes, and by looking or trying to find a solution for the system, what we're trying to do is we're trying to see if these three planes intersect somewhere. And we can see that they intersect at exactly one point, and that one point happens to be the origin. Can you see? What would be a good picture to put in our notes? Well, I know, that's why I'm putting it in our notes. Okay. It's better if I type things up instead of trying to write by hand. But I'm hoping that by now you're used to my writing. What? Trivial. Videos. That's what the videos are for. So the videos are for clarifying my handwriting and going to sleep. All right. Another example. So let's do another example that gives us a non-trivial solution. And we'll see why this is guaranteed to give us a non-trivial solution. But you might know. Why do you think this would guarantee us a non-trivial solution? Matt? So 2 equations and 3 variables. Yeah. Allie, were you going to say the same thing? Similar? Maybe. Well, yeah, we'll see. All right, so this is another homogeneous system. Homogeneous, it's all equal to 0, and let's write it. And now this thing, furthermore, as it looks, the shape of it looks different because what's going on here? The shape of it looks different because there's only 2 equations and 3 unknowns. And so if we were to do this, we get minus 5, 7, 9, and 1 minus 2, 6. So if we do a row reduction move, and I'm probably gonna, I don't know, multiply by 1/5. That's gonna get some fractions and stuff, but let's do it anyways. Or maybe we could switch the rows. So let's switch R1 and R2. Oops. 1 minus 2, 6, minus 5, 7, 9. And then so we got multiply the first row by positive 5 and add it to the second row. So the first row will stay the same, and this is guaranteeing the 0 for the first column in the second row, and then now we got to do the work. Minus 10 plus 7 is negative 3, and then 30 plus 9 is 39. Okay, so again, we could go on and continue working and making it row reduced. Should we do that? 39. Can't you tell it's a 39? Sorry. Yeah. Yeah, if we divide it by -3, that gives us more opportunities to use some of the other, um, yeah, the second row. Um, Gives us an opportunity to use more of our elementary row operations, right? So 1 minus 2, 6, 0, 1, and then -3, -13. And then if we want, we can back solve and let's go ahead and do that. Let's multiply the second row by +2 and add it to the first row. So 1, 0, -26 plus 6 is -20. Okay, so we have our free variable. So we have a free variable here, and then we can find solutions for this. So this is supposed to be, so we'll call this, wait, that's not free. What's the free variable? The third one, right? So x3 is free. So our third variable is free. And then now if we back solve, we can help solve for x2 and x1. So according to the second row, x2 is equal to -13 x3. So x2 is equal to, wait, x2 minus 13 x3 equals 0. And then so x2 is equal to +13 x3. Did I do that right? Right? Okay. And then x1, I'll put boxes around where I have x something equals to, so that I'll know that's my solution. And then from the first row, I have x1 is equal x1 minus 20 x3 is equal to 0. So x1 is equal to +20 x3. I'll box that as well. Whoops, whoops. Okay. So what is this, and how can we describe the solution set that would make this work? Well, first of all, let's imagine this, since we can still picture this, let's imagine this as something that's happening. This is in R3, x1, x2, x3. So that's like your x, y, z. So this is happening in three-dimensional space. What's going on here? What do we have, and what is the solution to this? Any ideas? You understand my question? Allie? You can, but I'm talking about the big picture, the actual picture. Sabrian, and that's not quite what I was looking for, Ren. It, it's an infinite number of solutions, and the line business, if you can expand on that a little bit, let's get so each of these equations are planes, right? That's all. And then these planes intersect. And if you imagine two planes intersecting, they will intersect in a line if they intersect. I mean, you can have two planes that are parallel, which don't intersect, but if they do intersect, these two planes will intersect in a line. And so our solution should describe the line that these two planes intersect. So let's first take a look at the graphics of this, since we have graphics. We have a -5 x. I'm going to have to do this over again. -5x plus 7y plus 9z equals 0. And then our second equation is x minus 2y plus 6z equals 0. So these two, so remember that if you have a homogeneous system, you're guaranteed the trivial solution. So these two planes intersect in a line, and that line goes through the origin. Okay, so that's our first observation, is whatever this intersection is, it has to go through the origin. All right, so now that we've established that, let's see how we can denote our answer. So what we have here, and we know vectors already, right? We're all experts with vectors already. So we can write our solutions as we have x1. So our solution is going to be, we're going to describe the solution as a vector x. So our x1 will have our 20 times x3. Our x2 will have 13 times x3, and our x3 is free. It's just x3, right? And well, x3 is common to all these components, so why don't we just take that out and factor it out and look at it as a scalar multiple of 20, 13, and 1. Okay, so writing your solution in this way is called a something. I can tell you what it is. It's parametric vector form. Vector parametric. Wow. I might as well just look since the answers. Parametric vector equation. Yes. Thank you. And this is usually a good way to describe a solution to a system that has free variables, because the free variables will act as a parameter. Okay, so it would act as a parameter, and that parameter will be, no, wait, what did I say acts as a parameter? Oh, your free variables. Your free variables act as a parameter, and we could call it x3, or we could just call it a random parameter, and usually parameters are denoted by t, and sometimes if you have two of them, you use t and s. So let's take a look at this. Let's take a look at the significance of 20, 13, and 1 as a solution to our system, and look at this in terms of the graph. So let's take a look at a vector. And a vector going from the origin to what? Pressing the wrong buttons here. Oh. 20, 13, and 1. That's kind of hard to see. But do you see what's happening with this vector? This vector is on the line that intersects those planes, right? So that makes total sense. But this is just one vector. So if we can write this as the parametric vector, and this is kind of a quick Calc 3 lesson on parametric equations. What we have here going on here? Condition is not appropriate after the comma. It's not. Is it R? No, it's not R. Oh well. So what I tried to do in this graph is to have a line or a point that walks through that line using this parametric equation. So for any value of n that I choose, that's like your x3, right? For any value of n that I choose, I will be on that line as I move through it. And so what we're doing is that we're letting n be the parameter, that's like your x3, and if you just scalar multiply the 20, 13, and 1, your solution, by some random parameter, then I'm going to get every single point in that line, which is a solution set. Okay? Does that make sense? I have to shrink this a little bit, and let's see if I can say what I just said again. So this is these are the two planes. I don't know which one is which, but did anybody see which one is which? Doesn't matter. So those are planes, and they intersect in a line. And we can describe this line as x is equal to 20, 13, 1 times some parameter t. In fact, we can say x of t equals erase. My eraser's not working. All right, need to erase. So we can express our solution as a parametric equation, and if we have a parameter t, we can treat it like it was a function. So that parameter t would be x of t, would be the number that you would multiply the vector by to get every single point on that line. So this is some random t. I'll now put t sub 1, a specific t value. That gives us a one single point, but then if we let t be whatever, then we can get whatever point on that line. Okay? Does that make sense? Do we have the connections? Right. Yes. So your solution is a span of one vector. So we can even say that. So solution is the span of 20, 13, 1. It's the span of that one vector. So when your solution is a linear combination of these things, you can look at it as a span. Okay. Questions? All right. Let's check out our next task, solutions to non-homogeneous systems. All right. So let's try to describe a non-homogeneous system. Non-homogeneous system is different from homogeneous system in that the non-homogeneous system has non-zeros on the right-hand side. That wasn't defined here, was it? So we have an equation ax equals b, where b is non-zero. Let's make a little note here. B not zero is consistent for some given b, then p is a solution. So we're assuming that we have a consistent system. Then the solution set of ax equals b is a set of all vectors of the form p plus v sub h. And what's v sub h? It's a solution to any solution is any solution to the homogeneous equation ax equals 0. So what are they saying? What they're saying is that if you have a solution to ax equals b, that's to say it's consistent, then that solution can be written in the form of p, which is a random solution, plus vh. What? Yeah. Say it again. Yes. Right. Well, VH could be a little bit more complicated. So VH could just be one vector, or if it's a trivial solution, remember it's a solution to AX equals 0. So if it's a trivial solution, then that would be 0. That's not a big deal. If it's a non-trivial solution, then it would be, we can write it in parametric form. And what we could do is we could just add this other thing. Right. Add the vector. Yeah. It should be one vector. It could be, the thing about this, when you said, Pedro, when you said what you said, you used the word the solution for this and the solution for that. Right, but it's not necessarily the solution, so it could be any solution to that. So I wanted to change that, but I thought it might have made things a little bit confusing. So Andrew, that idea that it could be any solution. So if your solution happens to be a line, it could be any solution that's on that line. Any solution that's on that line, yes. Yeah. All right, let's see if we can use the other examples that we just used. Example 3. All right, let's see. Let's take our previous example and change it to make it non-homogeneous, since we have the solution to the homogeneous system. And let's change it to a non-homogeneous. So let's pick some numbers here to replace 0. What should we pick? I don't know. Throw out some numbers. No, we're replacing this. We're shifting these planes so they don't intersect at the origin anymore. 26. That seems too high. 1 and 2. Thank you. What? So let's take a look at the graph of this first, and then we'll explore the actual solution. So would that work? That looks like a 3. That was a 3. All right, so let's take a look at the graph again. It's hard to see, but if I zoom in, can I zoom in? Zoom in. If I zoom in, I see that these two graphs don't intersect at the origin anymore. Okay, so that's one piece of information that's important. And if I kept this vector that I had before coming from the origin, I see that that vector I see that that vector is not in the line of intersection anymore. Okay, so those are a couple of things to notice graphically. And now let's dive into this and see what we can get out of the solution. So our solution then, because this is non-homogeneous, we will want to include the augmented part. So we got minus 5, 7, and 9, and then 1. 1, minus 2, 6, and then 3. So we include the augmented part and go through the same steps, which is probably why somebody suggested that we make this into a 3 instead of a 2. So. Oh, it should be 4? All right, well. I don't know. All right, let's see. Oh, we switched, right? We switched the order first. So let's switch the row 1 and row 2. 1, minus 2, 6, 3, minus 5, 7, 9, 1. And now let's do 5 times row 1 plus row 2, replace row 2. And then here we get, I forgot the numbers, so 10, negative 10, 7, minus 3. Negative 10, 7, minus 3. 30 plus 9 is 39. And now we have this 5, 15 plus 1 is 16. Okay. And then it looks like best way to solve for this is maybe to divide by 3, and so here we're going to get a fraction. Negative 1/3 R2 will give us 1, minus 2, 6, and 3 on top, 0, 1, negative 13, and negative 16 over 3. So keeping in mind that this is some augmented part, we have x1, x2, and x3. So x3 is our free variable, which we knew that. And then let's see, x3 is free. Let's do this in a different color. So then now our solution is going to look a little bit different because there's an augmented part. We're going to have x2 minus 13x3 equals negative 16 over 3. And so if we solve for that, x2 is equal to negative 16 over 2 over 3 plus 13x sub 3. Is that right? Okay, we didn't reduce it all the way, so we're going to have to do a little bit more work here now. Let's box this, and now to get x1 minus 2x2 plus 6x3 equals 3. So x1 is equal to 3 minus plus 2x2 minus 6x3. Now we know what x2 is, right? x2 is this big mess. So x1 equals 3 plus 2 times minus 16 thirds plus 13 x3 minus 6x3. Just algebra. That's x2, right? And then now I can simplify a little bit. So I'm going to have 3, and then this is 32 over 3 plus 3, or minus. Yeah. Can you do that in your heads? Negative 32 over 3 plus 3. Minus 23 over 3, right? 9, yeah. Minus 23 over 3. And then 2 times 13 is 26. 26 minus 6 is 10, right? 20 plus 20x. Okay? So, if we take a look at the solution and write it in vector form, parametric vector form, then it would look something like this. Our x1 is going to be negative 23 over 3 plus 20x3. Our x2 is minus 16 over 3 plus 13x3, and our x3 is free. So x1, x2, x3 in your vector form. And now we notice that, well, this is like addition and scalar multiplication, right? If you look at the last component there as 0 plus x3, there's a 0 constant along with negative 23 over 3, negative 16 over 3. So maybe we can split that up into two vectors, negative 23 over 3, negative 16 over 3, and 0, plus, guess what this is? 20, 13, and 1 multiplied with x3. So what we have here is a solution. This vector is a solution to the system, and this vector times x3, or times some parameter, is a solution to our homogeneous system. So note that we have a solution to, this is just one random solution, right? We could have picked any other. There might have been a chance where we would have gotten a different point, maybe. But this one is a solution to ax equals 0, the homogeneous counterpart. You know? Yeah. So this is what draws the line, and this is the shift. So this is, we can say this is a line from this particular problem. Now your problems might not all look like lines like this. It might, I mean, the solution set might be more complicated or it might be simpler, but in this case we have a line as a solution, and this is the shift from the line. So let's take a look at that graphically. I know this is probably not the best example to look at the graph of because it looks complicated, but let's take a look at this. We have a vector or a point negative 23 over 3, negative 16 over 3. Let's look at that in the graph. Negative 23 over 3. Negative 16. 1 or 0? 0. Is that anywhere? Where is it? What's 23 over 3? Oh, there it goes. It's on the other side. Right? But this it doesn't pass through right there. It doesn't pass through. Remember the black dot is would be the points that would go to our homogeneous system, right? And it doesn't pass through. So now let's actually take a look at that new line that they got, which is this thing plus t times the other thing, right? So these graphs are getting complicated. Sorry. Oops, I didn't want to do that yet. I wanted to do an XYZ. So this time I'm actually going to draw a line. That point plus the vector, what was it again? 20, 20, 13, and 1. And this time I'll multiply it by t as our parameter. And what this is going to do is I'm going to let t go from minus 3 to 3. And so that yellow line, there's a couple of things that's going on here. The yellow line is parallel to the original vector, right? Because they're both going in the same direction, 20, 13, and 1. The yellow line will pass through that point because that's how we define the yellow line. It passes through this point, it passes through the green point. And maybe the yellow is hard to see. Can you guys see the yellow? What color? Red? So that line is now the solution to the planes intersecting. And I don't know if you can see where the planes actually intersect, but let's see if we can see it. That's where the red line is. But let's actually take a look at the planes. There it goes. You can see that plane actually intersects. So I don't know what the best view is of this graph to put in our notes, but wait, what time does class end? All right. So, yeah, I don't know if this picture is going to make sense in the notes, but it'll be in the notes. And if you want to print it out or pull it out on your computer and try to figure out what the points are and what the black point, the green point, the two planes, and the blue line and the red line. Of course, it comes on the other side and it's not red anymore. I don't know what happened. Anyways, you guys can figure it out. All right. So that's the non-homogeneous portion. And like it says in the theorem here, that point P is actually in the intersection, or in this case in the intersection, but that point P is actually a solution to the non-homogeneous part. And then if we can find the solution to the homogeneous part, then we know just to add those two things. Okay? Any questions? Yes? Um, no, you could just go straight to the non-homogeneous part because you could see, I mean, if you're going to do both, then you know that part of your answer is going to be from the homogeneous part. But if you're not going to do the homogeneous part, you're actually going to find your answer here anyways. Yeah. All right. If we take a look at our first example where they intersected at a point, then what do you think your solution is going to be? It's just another point. It's not that one point, because remember this point is at the origin, and if it's non-homogeneous, then these three planes will intersect at some other point somewhere else, and that would be your P. All right. Oh look, there's an algorithm. What's this say? So let's see if we can summarize what we were just doing for finding solutions for non-homogeneous systems. What we want to do is we want to row reduce the augmented matrix. We did it with row echelon form, but if you go all the way to reduced row echelon form, then you would get the answers more immediately. Express each basic variable in terms of any free variables appearing in the equation. So we did that. So it got a little complicated here because we didn't use the reduced row echelon form. And so when you don't use the reduced row echelon form, then you're going to have to deal with extra variables, and this kind of substitution that we did from here. What? From here, when we let x2 equal to that expression that we found, because we didn't do the reduced row echelon form, then we have to do these other substitutions until we get it to the reduced row echelon form. So write a typical solution for x as a vector whose entries depend on the free variables, and then decompose x into a linear combination of the vectors with numeric entries. This is your p vector, numeric entries, and then using the free variable, extracting out the free variables in any of the other vectors that you have. Okay, and once you do that, then you have written your solution in vector parametric or parametric vector? Parametric vector form. Okay? All right. Let's see. Let's shift gears and go jump into section 1.7. Because if there's anything else that you really, really need to know in this class is you need to know the definition of linear independence. So we have a set of vectors in Rn, v1 through vp. It just means some other number. It's said to be linearly independent if you can write the linear combination of those things and set equal to 0. And the only way you would get this to equal to 0 is that if all the weights, x1 and x2, all the way to x sub p is equal to 0. So that's what it means to be the trivial solution, is that the weights in this linear combination is all set equal to 0. The set is dependent if there exists weights that are not all equal to 0. Some of them may be equal to 0, but not every single one of them is equal to 0, such that, and then the linear combination can be set equal to 0. By linear combination set equal to 0, I mean the 0 vector. And the other zeros that this is referring to is that the weights are equal to 0. That's just 0 scalar, because the weights are just scalars. So the idea of linear independence is really important here. And then in the real math class, I mean, in a more theoretical math class, let's put it that way. In a more theoretical math class, they would be doing a lot of proofs in proving things are linearly independent. And that's how, usually in a more theoretical math class, the first thing that they would talk about is vector space and vectors and vector spaces. And then they would talk about linear independence of vectors in vector spaces. And then they would have a bunch of proofs in proving things are linearly independent. Okay. So if you're a math major, that's what you're going to be going into when you take your next linear algebra classes, proving things, a lot of things are linear independence. I mean, you're going to be doing a lot of things, but that would be one of the first things that you're going to be expected to do. As a non-math major, who cares? What is important is some consequences of things that are linearly independent or linearly dependent, and that fits in with the stuff that we're talking about. You know, systems right now. Later on, we'll talk about other things, but the idea of linear independence is important. So this is how they define linear independence. And then we can immediately relate that to matrices by saying if the columns of a matrix A are linearly independent, then you only get the trivial solution. And that's an important piece of information. This is when it becomes more relatable to non-math people. Okay, so we can kind of take a look at play around with the idea of what it means to be linear independence in a like a common sense way by looking at, like, maybe if we have two vectors. Oh wait, the theorem 7 is kind of complicated. Let's do what I was saying. Two vectors. So if you have two vectors, if they're linearly dependent, can you give me an example of two vectors that are linearly dependent? We could be in R2. Let's be in R2 because that's easy enough to do. So vectors 1, 2, and 2, 4 are linearly dependent. Okay, what does that mean to be linearly dependent according to the definition that they have? That means something times 1, 2 plus something times 2, 4 can equal to 0, where I can pick two numbers for these blank spaces that would make this thing equal to 0. Two numbers that are non-zero. I mean, clearly, in these blanks, I could put 0 and 0, and then I would get this to equal to 0, and then I'm done. But the question is, can I pick two other numbers that are non-zero that would make this true? And can you find me a couple of numbers here that would work? 2 here and negative 1 here, right? So those are weights. So we could say C1 equals to 2, C2 equals to negative 1, C1, C2, not both 0. We'll make this equal to 0, and so therefore it's linearly dependent. Now, can you give me examples of two vectors that are independent? 1, 0 and 0, 1 are linearly independent. That says independent right there. Does. If you squint, watch the video. All right, so 1, 0 plus something times 0, 1 is equal to 0. Now, what two numbers can I put in here so that these two things are equal to 0? Is there anything else? There's no other numbers that I can put here except for 0 and 0. C1, C2, both have to be 0 for this to work. What? As only the trivial solution. Now, geometrically, can you imagine these two vectors? What makes two vectors linearly dependent? Yeah. They're parallel to each other, right? They're like a scalar multiple of each other. And if they're not, then they're independent. Okay, dealing with three vectors is a little bit more complicated, but you can visualize that in R3, and that's what we're going to try to do next time. I'm stopping a little early because I want you to be able to, if you didn't go yesterday already, go to the open house at the Learning Center. So for 1 point, 1 free point on your next exam, you can go to the Learning Center and pick up one of these things. In the back, there are 2 columns for you to get signatures. The first column is a STEM column, and the second column is a Learning Center column. I want you to get the signatures for all 5 of the STEM columns here. Okay, so go to the Learning Center, pick up one of these things, go to the back of the Learning Center, and talk to the STEM people with the peer mentor scholarships, etc. Okay, and so wait. So you have to have your name, you have to pick up this paper, save it, put your name up here, and then give this to me on Wednesday. We don't have school Monday. So, what? Yeah. Wait, it's next Monday is Labor Day, right? Yeah, so we don't have school Monday, so I'll see you Wednesday. So bring this on Wednesday, signed with your name on it, and you'll get 1 point on the test. Labor Day. All right. See you guys, and you guys will probably have another quiz on Wednesday when you come back. Yeah. On this stuff in the section before.